Hi everyone, I am Chen Lin from TSMC, IIP Division. It's my great pleasure and honor to present the paper, especially through the very special and well-organized virtual conference. My presentation topic is SOIC for low-temperature, multi-layer 3D memory integration. In this presentation, I will first provide an overview of wafer-level system integration technology. Then, I will introduce the TSMC SOIC technology by explaining and emphasizing how and why SOIC technology is now playing a key role for 3D heterogeneous integration. I will also provide electrical data which support the development of low-temperature SOIC bond for multi-layer staking. Lastly, very solid reliability data will be reported to support the newly developed low-temperature SOIC technology. To perform advanced heterogeneous integration, TSMC has provided wafer-level system integration technologies as 3D system integration platform, such as wafer-level CSP, InFO, and CoWoS. For the desire of high interconnection density, high bandwidth, and high power efficiency. However, the I/O pin counts of the conventional flip chip staking have been limited by the bump size, which is difficult to scale beyond 10 micrometer pitch. Furthermore, the interconnection of scale micro bumps with underfill may increase the parasitic capacitance, resistance, and inductance, and may degrade the device and power performance. To solve the problems, we develop SOIC technology to perform wider coverage of wafer-level system integration without solder bump, with ultra-thin bonding interface and high pin density. So, what is SOIC? It is so-called System on Integrated Chip. Our team first reported SOIC technology in the ECTC conference last year, 2019. There are three main benefits of this technology. SOIC is front-end 3D heterogeneous integration, and it can well leverage front-end tool capability, which is different from back-end 3D IC, such as wafer-level CSP, CoWoS, and InFO. SOIC is also available to support both chip-on-wafer and wafer-on-wafer process, which offers higher flexibility of staking process. Especially, wafer-on-wafer staking can simplify staking process with more attractive cost. Most importantly, SOIC allows mixed and matched heterogeneous integration for chips, wafers, and process. For example, it allows the integration of different chip sizes from different wafer sizes, no matter they are 6-inch, 8-inch, or 12-inch. Also, it has wider technology coverage across different functional chips, such as logic, memory, sensor, active, passive, 3.5, optical, biotechnology, and etc. Besides, SOIC is very friendly to integrate with back-end 3D IC. Moreover, it can easily integrate with products from third party, such as DRAM and CIS product. This slide shows brief comparison of integration flow between typical 3D IC and SOIC package. The staking of typical 3D IC depends on micro-bump-based structure, and so the bump pitch is constrained, whereas SOIC bond is a bumpless structure, and the bonding pitch can be controlled within few micrometers or even sub-micrometers. The SOIC technology does not require the underfill process. It can simplify the process flow and material. SOIC staking is available for wafer-on-wafer process. We are very optimistic on this technology and currently under development. Compared with conventional microbump-based 3D IC, there are several advantages of SOIC bond in terms of bonding density, electrical, power, and thermal performance. In the left figure, it shows by the application of SOIC bond, the bonding density can be boosted by 10 times or even more than 1,000 times compared to the typical 2.5D or 3D IC. The major reason is because of the significant shrinkage of bonding pitch by using the SOIC technology. In the middle figure, to ensure the high quality of signal integrity and power integrity, the interconnect wiring parasitics of resistance, inductance, and capacitance were analyzed and compared. It shows SOIC bond has smaller R, L, and C compared to the typical 3D IC bump. As a result, the SOIC bond outperforms typical 3D IC micro bump significantly in RC delay and IR drop. Regarding the power and thermal performance in the right figure, the SOIC bump also has strong advantages on the reduction of energy consumption per bit and the reduction of thermal resistance. After the review on the strong foundation of SOIC technology, here I would like to introduce our newly developed low-temperature SOIC technology for 3D integration. We focus on its potential application to multi-layer memory stacking, including 3D DRAM and 3D SRAM, which we have achieved 4-high, 8-high, and 12-high staking. Figure A shows typical integration of HBM cube and SoC die onto a CoWoS platform for the application of HPC products. In Figure B, it shows why the newly developed low-temp SOIC has great potential and strong benefits to replace the conventional microbump-based 3D IC. First, the low-temp SOIC integrated DRAM memory cubes can offer higher memory density, high bandwidth, and better power efficiency. Apart from that, the integration of the SoC with SRAM memory cubes using the 3D SOIC technology can enable higher system performance, as it is boosted by providing extra memory cache. When we talk about high-performance chip for AI or 5G, the bandwidth density and power consumption of 3D memory are highly considered. In this table, it shows the simulation comparison of system performance between a typical microbump 3D IC and a low-temp SOIC with 9-tier multiple staking, including a logic die and the 8-high DRAM dies. It shows the low-temp SOIC outperforms the typical 3D IC by 17% and 36% in bandwidth density when the low-temp SOIC die thickness is at 45 and 25 micrometers. And the power consumption can also be reduced by 9% and 19% respectively. It means the low-temp SOIC memory offers better lead form factor, higher bandwidth, and lower power consumption. To validate the stability of the low-temperature SOIC, in the lab figure, we examine the same daisy chain on the different 4-high SRAM samples. It shows very steep off-chain resistance accumulation line, which indicates the chain resistance across different 4-high SRAM cubes is almost the same. Apart from that, in the right figure, we also measured different lengths of chains within the same 4-high SRAM cube, and it shows linear behavior between those chains. The results tell us the uniformity of low-temp SOIC bonding quality across wafer and the robustness of bonding quality in long-chain connection. When it comes to low-temperature bonding process, people might have concerns over the bonding contact. The figures here show our developed low-temperature SOIC bond is an ohmic contact and is able to achieve linear IB behavior for long interconnection chain. Most importantly, the slope of the linear IB behavior of the low-temp SOIC bond is comparable to the one of high-temp SOIC bond. Moreover, the linear IB behavior was also obtained when tested on the same chain between different stack layer numbers, including 4-high, 8-high, and 12-high DRAM staking. From the results, it demonstrated the stability and capability of the low-temp SOIC technology for multi-layer 3D memory staking, which we have achieved 12-high staking and are under development of higher number of staking layers. To evaluate the reliability quality of low-temp SOIC bond, the breakdown voltage and temperature cycle test were measured for the through-via connection in both 8-high and 12-high DRAM memory. In Figure A, it is the accumulated breakdown voltage data for 8-high through-via connection from different samples, and Figure B is the data for 12-high through-via connection. Those samples had similar breakdown voltage. The results demonstrated the structural integrity of long through-via chains built by low-temp SOIC bond, no matter they were 8-high or 12-high 3D memory cubes. The chain resistance for the through-via connection in the 8-high and 12-high samples were also measured. The resistance at the time 0 and the resistance after running 200 cycles of thermocycling test B were measured and compared. The resistance results were shown in the left figure for 8-high and the right figure for the 12-high DRAM cubes. It is clearly that the curve of TCB 200 cycles match well with the data of time 0, which indicate the low-temp SOIC bonded chain is very reliable, no matter they were 8-high or 12-high 3D memory. Here, we demonstrate images from the 4-high, 8-high, and 12-high DRAM staking made by low-temp SOIC, including a 3D X-ray image from the 12-high structure. This brings strong confidence that the robustness of low-temp SOIC technology has great potential to be applied to the 3D memory, especially to the HBM. Here shows conclusions for SOIC technology in general and low-temperature SOIC technology for multi-layer 3D memory. For SOIC technology, it allows mixed and matched heterogeneous integration and can offer much higher I/O bonding density with lower electrical parasitic in RC delay and IR drop. It's also available for both chip-on-wafer and wafer-on-wafer process, and is very flexible to integrate with back-end 3D IC such as wafer-level CSP, CoWoS, and Info. For our newly developed low-temp SOIC technology for 3D memory, it provides low thermal budget process. It can offer both higher bandwidth density and lower power consumption, which outperforms the microbump-based 3D memory. Stable and robust electrical performance can be achieved for long interconnection chain. Most importantly, we have successfully developed 4-high, 8-high, and 12-high DRAM staking, and also 4-high SRAM staking. Starting from the conventional package, we have developed CoWoS and Info technology as back-end 3D IC solution. Now, we have successfully developed SOIC technology, including high-temp and low-temp SOIC, for front-end 3D IC integration. Especially, SOIC technology can be applied to both chip-on-wafer and wafer-on-wafer process and leverage advanced process node such as N7, N5, and further. This provides very high flexibility and high-end 3D integration, which can be easily integrated with back-end 3D IC package. As we know, the market for 5G, AI, and biotechnology are booming. TSMC's wafer-level system integration technology provides flexible and reliable solutions to meet customers' demand, such as AI, HPC, mobile, IoT, and automotive. TSMC is not only the first and now, but also the ultimate system integration foundry. Finally, we would like to acknowledge TSMC front-end and back-end fabs, product engineering, quality and reliability assurance colleagues for their good support and contributions to the paper. Thank you for your attention.